Hello everyone, welcome to my talk, Optimal Residential Battery Storage Operations Using Robust Data-Driven Dynamic Programming. This project was finished by me, Dr. Leibowitz, and Dr. Hans Sutanto from the ORIE program in UT Austin. Here is a brief overview of my talk. In this project, we studied the stochastic control of the operation of residential battery storage under multiple uncertainties. We developed a data-driven dynamic programming model to minimize long-run electricity costs. We also constructed two robust data-driven dynamic programming models to mitigate the overfitting in the DDP model. And last, we tested our algorithms on real data and compared with cellback programs. Residential PV capacity have grown rapidly over the past decade and are still playing an increasing role in nowadays electricity market. However, the intermittency and uncertainties of the PV brings a significant challenge to both household and utilities, and storage technology can be a very good solution to mitigate such issues. The effective operational strategy for PV battery systems have a few advantages, including improve the efficiency of power usage and reduce the electricity bills for the customer, and it can also accelerate the market uptake of the PV battery system. So in this project, we considered household with electricity usage and generations, and he is facing a time-varied price. The development can be described in the figure. At the beginning of a period T, the customer will obtain a battery storage level ST, and next he will observe uncertainties of price, usage, and electricity generation. Then he need to make a decision on the charging or discharging of the battery. And after that, he can, at the beginning of the next period, T+1, he can obtain the storage level of the battery as T+1. Assume that battery runs in a circle and the cost will be incurred by purchasing electricity from the utility to meet the usage. The problem can be solved by a dynamic programming procedure, and we can write the Bellman equation of the dynamic programming like this. Here, Vt is the cost to go function, which is a function of the current storage St and the current and past uncertainty capacity. That is equivalent to the minimum of the electricity purchased at the period T and the conditional expectation of the cost to go function Vt+1 under the current observed uncertainty capacity. The constraint will include the supply and demand balance and the maximum battery capacity constraint. If we can calculate the cost to go function backward for T equal to capital T to 1 with a terminal condition, here Xi represents the vector of the triplet of the exogenous parameters. There's a problem on evaluating conditional expectations since it is usually intractable. So we have solutions using the empirical estimate probability distribution from historical observations, which can reduce the infinite space to a discrete finite space I from 1 to n. By replacing the conditional expectation, we can get a new formulation of the past cost-to-go function. And this, we only need to evaluate the cost-to-go function at historical data point. The method we use to generate such empirical probability distribution is the KNN learning algorithm. This is the formula on how we calculate the nominal probability distributions. And this is a brief example. If we assume that the uncertainty is a two-dimension vector, then we have 7 historical observations, and we need to choose some of them that are close to the current uncertainty cosine p and neglect the others. We use a dynamic capital KT to determine the number of historical select historical observations at every period t. And this is the next part of the example and shows how we normalize the empirical distribution from the probability without gain to the probability with gain. And if we revisit the empirical estimate in the DDP formulation, that is easy and trackable. However, there's a common problem which often exists in the machine learning problem, that we need to mitigate the overfitting phenomena in the training, and to minimize the difference of the performance on the training set and the testing set. So to solve the issue, we can construct an uncertainty set, and instead the empirical estimate, we can consider the worst case estimate on the probability distributions in such uncertainty sets. So we can construct an uncertainty set P epsilon phi like this, where T hat is the nominal distribution and P is a random variable. And the second formula represents the worst case estimate rather than the accurate estimates on the nominal distribution. So by applying this method, our calculation will be more conservative and less vulnerable to the estimation errors. We define the uncertainty set like this, and the key question is how to define the function phi as the distance matrix between two probability distributions. We can use the chi-square distance, and which yield the final formulation we call the CRDDP. The chi-square is defined like this between the new probability P and the nominal probability P hat. And the final formulation will lead to ON second order Cohen constraints, which can be solved by convex 2 effectively. We can also use the Wilson string distance, which also consider the geometric properties on the historical observations. The Wilson string distance can be expressed as the linear programming model, and the final model will lead to ON square linear constraint. We test our algorithms on the real-world data, and we use the data from homes in the Moore neighborhood in Austin with solar PV panels. We also use the time-varied electricity price from ERCOT in Texas. We used the data in 2016 for training the Haskell function and the next year data to test our performance. We also include some benchmark. The first is TVA heuristic and ADP, the approximately dynamic programming based on the Markov decision process. We also include the scenario of perfect informations and the case that the customer do not have a battery. The table shows the performance of different algorithms, and we can see from that our DDP algorithm outperforms the other 3 cases on both the average cost increase over PI and the 95 percentile cost increase. And compared to the DDP, the robust data-driven, dynamic data-driven programming also improves a little bit on both metrics, which means that our algorithm is successful. We also did some sensitivity analysis. The first factor that can affect the performance of our algorithm is the maximum capacity of the battery storage. This figure shows the relationship between the performance and battery storage capacity. We can see that for the TDP and TBA algorithm, generally the performance of the algorithm will decline when the battery storage capacity increased. But such phenomena is not significant in the CRDDP and WRDDP, and that shows the RDDP will successfully mix to mitigate the overfitting phenomena. Another factor which is very important is the robustness parameter epsilon of uncertainty set. It can determine whether the uncertainty set is too big or too small. The result is very interesting. For the chi-square distance, the trend is very clear, and we can get the optimal epsilon based on the cross-validation, but the cross-validation may not be very effective for the WRDDP because the Warsaw-Thin distance is more complex, and which also consider the geometric property of the historical observations that is really dependable on the what training set we have selected. And last, we did a case study on the comparison between our algorithms and different cellback programs. We construct two programs. The first is FIT, which assumes that the utility are forced to purchase all the generation from the customer at a fixed price gamma, and the customer cannot consume their generation locally. Second is net metering program, which allowed the utility to purchase the net excess generation from customer, and the customer first consume their own generation before purchasing electricity from the utility. This figure shows the comparison between the different algorithms. The horizontal line represent the case of no battery and the two cellback programs. We can see that our algorithm improved the break-even battery cost for almost $200. And what is interesting is that if we combine the cellback programs FIT with our algorithm CRDDP, which is normally forbidden by the utility, we can see that the break-even cost will be smaller than the vertical line, which is the current capital cost of battery storage, that is 488 per kilowatt hour. And come to the conclusion, in this project, we develop a data-driven dynamic programming model that minimizes long-run electricity costs by stochastically controlling the operation of a residential battery storage under multiple uncertainties. We constructed two robust data-driven dynamic programming models to mitigate the overfitting phenomena in the DDP model. Thus, we tested our algorithms on real-world data and compared them with a feed-in tariff of net metering program. The future direction includes combine our algorithm with more cellback programs or extend the time cycle to a week, a month, or even longer period. And this is some main reference that was cited in our project, and our project has been published by the IEEE Transactions for Smart Grid. And thank you for listening my talk. And if you have any questions or suggestions, please feel free to contact me. Thank you.